Okay, hi everybody. I'm very pleased to be here tonight, especially because 4 years ago I started my first internship in data science in the Palais Brognard. I was working for the Institut Louis Bachelier. I don't know if you know that institute, but I started there 4 years ago, and right there I am now at Quantmetry, and I'm going to talk about fraud detection. So first, is there anybody who knows about Quantmetry? Maybe raise your hand. Okay, great. We've been doing data science since 2011, and we are currently around 100 consultants. So data scientists, data engineer, ML engineers, data consultant. One thing we have in particular compared to other companies is that we are doing research and development. So around 20% of our time is dedicated to research and trying to stay at the state of the art. So we have multiple references across all those years, and we have worked with a large portion of the CAD count. So today the main topic is about fraud detection. So currently I'm more working on the computer vision side. My last project is actually about pose detection, so finding key points on a body of a human, for instance, which has applications in finance also. If, for example, if you want to detect if there is an intrusion or somebody is trying to break an ATM, so un guichet automatique bancaire in French. But I've worked also a lot in the banking industry with credit card and transfer fraud detection. So there are several types of fraud. I won't go into any of all of them. Mainly it's internal fraud or external fraud. But what is very interesting is that every single one of them is kind of connected to each other. For instance, well, you might have just a fraud on non-cash payment over internet. But you might also have hacking of the information system resulting on such a non-cash payment over internet. You might also have a bank check, for example, a check deposit on a bank in another region, and following that deposit of a check, you have a money transfer to the fraudster bank account. So two types of frauds are connected, one after the other. So that's something to keep in mind. So basically, one tip I could give you is like, you need to fight fraud in a global way, and fraudster will always focus on the weakest point of your system. So be sure to cover everything. So we have a little picture here, which is kind of funny. I mean, if you lock the middle of the road with a lot of stuff, but you let some key elements of your system unprotected, they will just avoid the big protection you set there, and it will be easy for them to break into your system. So first, an example about credit card fraud detection. Imagine you are a customer, so you have a credit card, you are making a payment on the internet. Could be about on Amazon. It's very different from if you're buying a ticket on WeSNCF, or if you're purchasing an application on the App Store. It's very different patterns of fraud, because when you're buying an application on the App Store, it will be small amount of money. If you're buying a train ticket, it could be on the phone. You have different systems to buy the ticket. It will be different amounts also. So you need to have specific modelization for each of those streams. One very important element also to keep in mind is that fraud is a very unbalanced problematic. So when we've dealt with credit card fraud, we had a ratio of one fraud for around 1,000 LC transactions. So if you want to modelize credit card fraud, what you could do is use current operation attributes, right? An operation is initiated, so you have the hour, you have the amount of this transaction, and many other stuff. And some of them could also come from the retailer. They are specific to the retailer. It could give you information about its system and maybe give you a score about its own perception of the danger in the upstream level. And then you add complementary data, which is coming from you guys. For example, what is the characteristic of my customer? Who is this guy? What he's doing? What its spending habits, etc. So you combine all of it. That's your input. Then you build a model. And what the output is basically a score, and you can calibrate the score so that it's a probability, which is not something evident at first. And so make it between, for example, 1 and 0, 1 being, okay, this transaction is a fraud, and 0, this is not a fraud. In credit card fraud, one very important parameter is it must be real time, right? You are purchasing something online, you don't want to wait like 10 minutes to get your good. Second example, transfer fraud. So in addition to a person or a professional, you can also have companies which are making credit transfers. If you are a person, you can use remote banking, you can go to an ATM, you can go to your bank also to do the transfer. If you are a company, you can use what we call electronic data intentions. It's basically a way to automatize your transfers to your suppliers, for instance. So it's very different elements. Usually, EDI is very well protected, so most of the fraud is coming from remote banking and ATM. Debit transfer fraud is not prevalent, it's more credit transfer fraud, which is the core issue at hand. The unbalance is much more important in transfer. You have a ratio of 1 over 100,000 LC transactions. What's very interesting, so you have the same kind of framework for, as we've seen in credit card transactions, but with transfer fraud you can add other attributes. So I've talked about check deposit. So check deposit is a main element in transfer fraud because some guys in the bank, they used to say, okay, you need to create money before transferring it somewhere else. So you need a fraud in check, for instance, to create that amount that you will then transfer to the fraudster account. You have also the phishing and the malware dimension, so you need to have a model upstream to find if there is an unusual behavior, if the guy is maybe typing his password a little bit too fast, and use logs information of your information system to identify those kind of weird behaviors. And that's your model. One important factor also is you have known real-time constraints at time, because with fraud transfer, when a transfer is initiated, you still have a few hours window to analyze what's happening, and to, if needed, you can do what we call a recall. So you do a recall, you send a signal to the banks the transfer has been sent to, and you ask them, okay, freeze the money, and we need that back because this is a fraud, and here is why, and you can get the money back. Okay, so now I'm going to talk about the best practice for modelization for fraud in general. And I will try to give you my recommendation based on what I've done and what I think is working, what I think is not working. Supervised or unsupervised learning. I've tried to modelize here, so green dot are LC transaction, red dot are fraud transaction. And if you build a model, a basic model, you might come up with a solution like this. So your model is correctly identifying the fraud over there. It's pretty simple, right? It's unbalanced. You have few red dots compared to the green ones, but it's a very easy problem because the red dots are on the side. It's not reality. Reality is much more complex. Reality might look like this. So I have a question for you now. What, in your opinion, would detect as fraud an unsupervised learning approach? So unsupervised learning is like you are not, it's if you look at those points with your human eyes and you think about the distribution of those points, but you don't know that the red dots are actually red, okay? What's, in your opinion, something unusual when you look at it? What are the points that are unusual? Yeah, right, those. This is a fraud. But actually, when you know the annotation and you know those transactions are actually frauds, and you can tell the algorithm, this is the fraud, the result will be very different. Could look like this, for example. So that just to illustrate, it's a very simplistic way of seeing things, but supervised allows you to target usually fraud in a better way. But one of the biggest issues is that you need to be sure about the labels. So the elements you are seeing as fraud to the algorithm. I'm going to give you an example. So let's take dogs and cats, so a very simple example. You want to distinguish between cats and dogs. If this is very simple like this, it's easy because it's the same example as over there. You can very easily detect cats compared to dogs. But if I add two more elements, which are those two cats, but I label them as dogs. So basically 50% of my labels are incorrect, which could happen in fraud. How the algorithm is supposed to make sense out of it, right? It's impossible. So hence, my next point. Data quality is mandatory, and especially in unbalanced problematics. So in fraud, you might have, let's say, 95% of valid transactions, and you reject 5% of them. It could be like the current model you have in your system. What is the reality? Maybe among all the valid transactions, you have 1% which is actually fraud, but you don't know it right then. Maybe you have to wait a few months in order to get the information. Maybe your client will call you and say, okay, or I've checked my account and this is a fraud, this is a transaction I've never done. And among the transactions you've rejected, maybe some of them are valid transactions also. But the only way to know it is to call your client and ask him, well, I've blocked your transaction, is that true? Is that correct? And then if you do it correctly, you have reliable labels and reliable information. But it is human time consuming, right? But you really need to do it in order to build a very sound and stable data set, which will be the base of your model. If you don't do it, you will just build something on top of something not reliable, and you will end up with very bad results. Something you can also do is use common sense. For instance, if you have fraud transaction very close in time to valid transaction, LC transactions, it doesn't make sense, right? Imagine you've bought two train tickets. One is a fraud. The other one, you just bought it like maybe 1 hour before, and it's LC transaction in your dataset. Doesn't make sense, right? So maybe what you can do is remove some of the valid transactions based on the assumption that all your frauds, you have investigated them and they are correct. So that's kind of undersampling your dataset. By the way, this is one of the methods I will mostly recommend because some guys are talking about oversampling your dataset using maybe smart methods, or I won't go into the details, but usually it's also about generating new data, but you need to be very careful about it because you need, well, first data to train your model to generate new data. And so in a way, you need to first understand the data in order to generate reliable data. You can then count on it. So it's quite difficult to do. My advice there is better small, but reliable data. So we're not talking big data. If you have small, but it's very reliable, some data, just use it. Then when you have the data, how do you train your algorithm? You have many ways of doing it. I will present you one method that I think is very interesting and very reliable. It's called nested cross-validation. So it's maybe the most technical slide over there. You don't need to understand all of it, but basically what it's doing is that it's making sure you have the ability to replicate the result you've observed on your validation data and making sure this result will stand still at least for the next month or upcoming events because you have no overfitting on your data, basically. Over there, you have the time frame. So on the left, it's past the oldest data, on the right, the current one. Imagine you have 1 year of data. You can start on the last from 12 to 6, the last 6 months of data. You train on that, then you validate on the next month. And then you do it again, you train on 7 months, and you validate on the next one. And then you do it until you reach your up-to-date data, basically. And that's it. And then you average all the errors on your test, and that will give you an average error over the past. And all the time you've trained on the past to test on something in the future, like in real-time constraint, right? And you don't mix everything up, because you could do a modelization out of time, but that's not what I present you over there. And of course, when you train, you do a training on a specific subset and you validate on another one in order to tune your hyperparameters. Then you want to analyze your results. Then again, it's because it's an unbalanced problem. You really want to have a focus on your metric and be sure that your data is understandable and you don't make your results better than they really are, right? Because some people do, and it's a bit annoying. So here is an example. So in red, again, fraud transaction, in green, healthy ones. The circle is a rule which is blocking all the fraud inside that rule. You have two metrics which I think are very interesting to present you here. It's called precision, which is the amount of fraudulent transaction you have among all the fraudulent the transaction you've blocked. So basically, you've blocked 3 frauds over there, but you've blocked also 15 transactions. So your precision is quite low, 20%. And recall is the total amount of money you've managed to block, fraud you managed to catch, actually. So you have 2 fraudulent transactions on the side. So that means you have a recall of 60%. Now let's try to make it a better rule, right? Maybe you want the rule to be more precise. You don't want to have so many people annoyed because you blocked their transaction, which were healthy. You can imagine another rule, which is a better one, I think. So this new rule is targeting a smaller set of transactions. And so you have only 6 transactions blocked in that new rule and 2 real frauds inside. So that means a precision of 33%. And what is a recall? So recall is the total amount of fraud that you manage to catch with respect to the total amount of fraud you have in your data. So here you have 500 euros, basically, of fraud, and you've catch 200, 40%. In my opinion, this is a better rule because your precision is higher, but the balance between the two is better. I've multiplied the number of transactions by the weight of it, and the weight is the amount of the transaction. Because you might want to understand, you could block maybe 50% of the fraudulent transactions, but in amount, it might be a small amount, right? Maybe only 10% of the total amount of the fraud. So it's kind of like you are focusing on the fraud with the largest amount of money. It's basically the same because all my frauds have the same amount in my example. But let's say, for example, that those 2 over there, they are not 100 euro, but they are, I don't know, 1,000 euro each. That would mean your recall would be very, very low because you didn't manage to catch the big 2 on the left. But in that example, I made it simple, so every transaction has the same amount. In this specific scenario, in a business standpoint, they didn't want us to put into production rules without a minimum threshold value for precision, actually. So we wanted to keep that information. So they didn't want to have a very high customer inconvenience. So they wanted at least 30% of precision. F1 score is great, but it's kind of a mean, and you kind of lose sense of what's happening when you also use it. That's a very good point for the next element I'm going to show you. If your precision is very high, so what's happening is that all the transactions you block are frauds. And if it's very low, you have a lot of customer inconvenience. If your recall is low, you detect no fraud at all. But if your recall is very high, you detect all the frauds. So basically, what you want to do is a good balance between the two, because of course you could over-prioritize one aspect compared to the other, but that would result in bad results. You could also have what we call a cost-sensitive analysis, which is basically optimizing your precision and your recall based on, for example, what is the cost of an investigation? What is the cost of losing a client? How much does it cost? Because if you block a fraud, it's easy, right? It's 100 more euro in your pocket. But if you lose a client, how much does it cost? Depends on the client, I guess. But you could optimize your recall and your precision based on how much does this client worth, and maybe I need to protect him in a certain way. So to sum up, you have a fraud detection system. So you have a transaction. You try to identify fraud and LC transactions. Then you investigate, you try to see whether the transaction you've blocked are real fraud or not. Then you label, and the faster you do the investigation, the better it is. The quicker you will have results, you could use again to train your algorithm. So you can do, for example, adaptive algorithm, and you try to adapt to what we call concept drift. So when the fraudsters are inventing new ways of targeting your system. You want to facilitate future investigation, and the system is always learning on new labels people are giving you. So the best way I see fraud in credit card, for example, or in transfers, for example, they send you warning on your web, application, on your mobile application, and they tell you, okay, is this a fraud or is it not a fraud? And you can answer immediately, and you have already a feedback with almost no cost for the bank, and you can feed that again in the system, and then you can block new fraud patterns very quickly. Okay, and my last point will be about interpretability and why it's very important. Two possibilities: either your algorithms are interpretable by nature. So if you use, I don't know, maybe decision trees, it's quite simple. But we've developed a package called scope rules, which is a mix between decision rules and random forest, which is interpretable. So you can use rules like variable 1 over a given threshold, I don't know, 200, and you block that transaction. Or you can use black box, what we call black box algorithm, but you can still use interpretable method on those using, for instance, sharp values, which is a way to give a weight for each variable explaining the output of your modelization. And it's a local interpretation, so you can give the client a reason why you've blocked its transaction and what was the reason for his specific case. 2 weeks ago, when my bank called me and said, okay, I've blocked your transfer, and I asked them why, they couldn't tell me, so maybe if they have interpretability in their models, they could have told me, and that would have been better, I think.
Do you use graphs for your also fraud detection? Because I had a presentation one time on the utilization of graphs, especially on the Ethereum, for example.
Okay. I mean, we've used graph, but not on credit card transaction, on transfer fraud transaction. And well, you have a lot of methodology you can use. You can cluster people depending on where they belong in the graph. You can also use connectivity strengths in between people. And in the banking industry, they strongly believe that you have key points, key people that can then send money to many other people. I don't know the word in English, but in French it's like mule. So people, we are taking the money and then using like intermediate people that will just distribute the money to other ones. So network analysis is very important also.
Thank you very much.